So 15.7 is on the divergence theorem, and so let me state the theorem here. Let F be a vector field with continuous first order partial derivatives and let B be a solid with boundary, with positively oriented boundary, and I'll just like we did before. So now we have a solid and it's got some boundary around it, okay? And so it's going to be a closed solid, and so the point, the positive orientation, we need to be sticking out of it. You should kind of think of this like Green's theorem. This is an analog of Green's theorem, right? When we were worried about Green's theorem, we said we had a curve, and we always assumed we were oriented positively around it, right? And the question was about the region, and then a relationship between the integral over the region and the integral around the positively oriented boundary. Same thing here, just now we're in three-dimensional space. So our boundary is the outside of this B, and then the B is the whole inside of this, whatever this guy is. That make sense? So you went from a closed region in the plane to a closed region in space. The outside is the boundary in both cases, the inside is the B. And the orientation has to be the same. Here it meant you went around counterclockwise. Here, positive orientation means you're sticking out from it, right? Okay. And so that's all that's being stated here. And so let's just say then the integral across the boundary of f dot, I guess I'm going to call it ds still, but it's the s is that boundary, right? So you're doing a surface integral, so the surface integral over that boundary. Remember what Green's theorem, what was the statement of Green's theorem? That the integral, the double integral over the region was equal to, of the region of something, right? The p, or the q sub x minus p sub y was equal to the integral over the line integral, right? And so we have the same thing. The surface integral is equal to, now it'll be a triple integral over the region, right? Because the B is a three-dimensional object. So you're taking the triple integral, and then we replace the q sub whatever with the divergence of your f. And so I think the book actually spends quite a bit of time trying to prove it. I don't think it's worth our time. I don't think we'll remember it weeks from now, and so I don't know how important it is. So let's just try to use it first, and if we have interest and time, maybe we'll go back and prove some stuff. And remember, this was what we called the flux too, right? So sometimes you'll just see it worded that way. So let's just try a couple examples and see how we do. So find the flux of f equal to this. Here's our function xy minus 1/2 y squared, and so on. So find that through the surface bounded by z equals 4 minus 3x squared minus 3y squared We'll look at what this looks like in a second. Make sure that everything's okay. Well, let me write it down. I don't trust what I wrote down. Bounded by this on the top, x squared plus, I don't trust myself because I can't read what I wrote. I'm going to assume that's what it is. X squared plus y squared equals 1. 0 less than or equal to z, less than or equal to 1. And I put on the sides. Let's draw this and make sure this makes sense before we do any work. And z equals 0 on the bottom. Okay. So before we apply anything with the divergence theorem, we want to get a feel for what this region looks like. And hopefully this isn't too bad. So what's z equals 4 minus 3x squared minus 3y squared? What does that look like? Yeah, so it's a paraboloid. So it's a parabola opening down, but at 3 dimensions, right? So let's just draw it up here at 4. And so you'll get this guy that falls down like this, right? And then we're telling you to only use this surface between
0 and 4.
Not 0, 1 and 4, right? So we're going to use this surface until we get down to a height of like 1, and I'll just guess that that's there. So we got this guy dropping down. So something more or less like that on the top. So I think our region looks okay. And then let me point out real quickly. Z equals 1. You get 1 equals 4 minus 3x squared minus 3y squared. That's x squared plus y squared is 1, right? So these two match up nicely at that height. Does that make sense? And then what's x squared plus y squared equals 1? It's just a cylinder. And so then you're just going to get a cylinder dropping down like this. If that makes sense. Is that okay? So you got this top here of z equals 4 minus 3x squared minus 3y squared. You have a bottom of z equals 0. And then around the side, you basically have that circle of radius 1. Does that make sense? Or that cylinder of radius 1. Okay. So I think everything's good to just apply the theorem now. And so, oh, and I didn't even say, through this surface, assuming assume positive orientation. So again, if you just describe a surface to someone, you assume the orientation's positive. If they gave you a parameterization, then you just have to check to make sure it's pointing out in the right way. So, but again, the point is, and you do the same thing, right? You negate your formula if the parameterization you were given was actually the negative, giving you the negative orientation of your surface. So anyways, we're after the double integral or the surface integral f dot ds. And we can just turn it into the triple integral of our divergence of f dv. All right, so let's just maybe come off to the side here. What's the divergence of f?
Minus 2y plus 1.
Minus 1/2
Oh, yeah.
of 2y, right? So just minus y plus 1.
Yeah.
So it simplifies down just to be 1. If there was more going on, that'd be, include that in here. Okay, now, if we want to integrate over that region, what coordinate system do we probably want to use? Yeah, cylindrical makes the most sense, right? Because you have a cylinder there. And so let's do that. When you integrate in cylindrical coordinates, what is the dv? Stretch off r, d, c, dr, d theta. theta. Okay, and so for this setup, where did the z's go from?
1 to 4. 0 to 4.
4.
Not just 0 to 4, but 0 to, what is it?
4 minus 3r squared.
Minus 3r squared, right? Because you got that paraboloid sitting on the top. So you just write that in cylindrical coordinates, and then you go from there to there. And then the rest of it's pretty easy right now. You just collapse down to that circle, and so it's 0 to 1 and 0 to 2 pi. Now let's just, we haven't done any of these, so let's do this one all the way. So the derivative, or integral with respect to z is just rz, right? And then you plug that in, so I'm just going to jump ahead. It'll be 4r minus 3r cubed. Is that okay? And then just finish off that integral. To r squared minus 3/4 r to the 4th theta and 0 and 1. 2 minus 3/4 d theta. 5/4 times 2 pi, right? 5/4 times 2 pi. And again, you can obviously clean that up. All right. Any questions so far? Okay. Let's try one more here. Okay. So this time, find the flux. Okay, so here's our integral. Oh, it's lazy again. I got this one canceling out nicely as well. Why do I keep making them work out so nicely? Anyways, let's type that up. Where, so the point is, whatever function shows up inside, you just integrate it. It doesn't get that bad. Where S is the tetrahedron with vertices Alright, so this one isn't, hopefully isn't too bad. So, take a minute, see if you can do the same thing we did for this one. I guess stay in rectangular coordinates for the whole problem.
That was
Tetrahedron, draw those points and then connect them with lines and
Oh,
whatever shape you
okay.
get them. Play around with it for a second. just talking about that. Does that make sense? So, let's do this. So you're integrating, so when you, again, and I didn't put it down here again. Assume positive orientation unless you hear otherwise through this surface. So we're going to go through this surface that's defined by this, right? But divergence theorem will let us switch the integral to be a triple integral over that solid. And so you're going to need to have equations for the solid, right? So you need to know what the what the plane is on the top, and then what the plane is on the bottom. We've actually seen this plane before. Oh, maybe we didn't see it exactly this way. You can guess what this plane looks like. What is it? So let me just write it this way. One way to do it would be to realize it starts at 3, right? And then you just need to know the slopes in each direction. And so it's minus some AX minus some BY. And so you could force it, you could figure out the equation from there. Another way might be this, if you've seen this one before, you might realize if I did 6x, 3y, and 4z equals 12, I get the right thing as well, right? Because then I'd get a x-intercept of 1, a y-intercept of 4, a z-intercept of 3, so that plane would work. So however you come up with the plane is fine with me. So we get what? Minus
3 minus
3 halves x and minus 3/4 z. Does that sound okay?
Y.
1.
Y.
Or y? That look okay?
So we divide by 3.
Divide by, oh wait,
By
yeah,
4.
divide by 4, right? Move the x and the y over, divide by 4. And so the 6/4 is the 3 halves, right? And so again, you could come up with that however you want, but when we integrate, we're going to integrate from what? 0 to this for our z's, and then we'll collapse down to the xy plane, right? Where we went through 4 and 2. And so in the xy plane, what's that going to be? Y equals
4
minus
2x.
2x. That makes sense? So those are all the pieces that we'll need. And so the divergence will just compute along the way. Like I said, it works out just like the last one did. So you get, this time I'll just write it in here, 2x minus 2x plus 1. We'll just do it this way, dv. And so we end up just integrating 1, and so it's dz. And we'll just do this order, dy dx. So what are my bounds here?
0 to 2. 0 to 4 minus 2x.
Oh, so it works from the outside. 0 to 2, 0 to 4 minus 2x.
0 to 3 minus 3 over 2x minus 3 over 4y.
Good. And then that's really easy, right? It's just fixed bounds, I guess we'll work through. 0 to 2, 0 to 4 minus 2x. So when you integrate with respect to z, you just get z, and then you plug in your function minus 0, so it's 3 halves minus 3 halves x minus 3/4 y dy dx. 0 to 2, 3y minus 3 halves y minus 3/8 y squared. Right. And so I guess it gets slightly ugly with that 4 minus 2x that you got to plug in, but hopefully it's not. So 0 to 2, 3 times 4 minus 2x minus 3 halves times 4 minus, oh, I left an x here. 3 halves xy, right? X squared, 2f x, 3/8, and then 4 minus 2x squared. 12 minus 6x
minus six x.
minus 6x.
Plus three x squared minus, 6 plus six x minus 3/2x squared.
All right, I think you're right, but you're ahead of me, let me think it out. 16, and then
Minus 16x.
16 x plus
4x squared.
4x squared, is that okay? And then multiply that through by the 3/8, and so you said you get what, minus 6.
Plus 6x and minus 3/2x squared.
Okay. That looks good to me. And you have that, and we're pretty much done. What do we got? Well, let's clean this up, I guess. You won't have to necessarily. So what do we have?
6.
In terms of x squareds, we have,
3/2x squared.
right, we have x squared, right? 3 of them minus 3 halves.
6x.
And yeah, so we just keep track of everything. Those cancel, so minus 6x, good. And then
Plus 6.
plus 6. Okay, good. So just keep track of everything, make sure you have accounted for it all. And so then you just get, what, x cubed over 2 minus
3x squared.
3x squared.
6x.
6x, plug in 2. 4 minus 12 plus 12. So 4. Okay. All right, so play around. I look at the homework. They don't get any more complicated than that. I mean, some of them just get, they can all get really messy, right? But there's nothing crazy clever going on. You just have to be careful and keep track of things. So I think I will just stop there for 15:07. Yeah, let me just stop there.